Oh my gosh. My upload is garbage. Well. Okay, it's getting better. Whoops. Okay. What do we try to do first? Okay, let's try to learn this. Okay. Burst balloons, where's that? That's graphs, right? Oh no, it's DP. There we go. Do I even know how to do the DFS version of this? Understand the tabulation solution. Let's see if I know the DFS way. So we get a left pointer, right pointer. Let's do 0. x equals dfs times table that's I minus 1 plus dx minus table plus 1. Good lord. What did I do wrong? Cool. So I know how to do this. It's slow as heck though. Jeez. Only 5%? So from my mic. That's not good. Let's check. Okay. So it's in table element. I think it's like and you have to actually make new nums. I think so length, Is it the same thing? You multiply by the right and the left. We have to multiply by new nums, right? Is this going to be new nums? New nums? Or is it like... This is definitely wrong. No, what the? Whoa, whoa, whoa. Did not mean to do that. N. Oh, one of this is like -1 or something like that. Yeah, I don't really know what I'm doing here. Why do you submit? Okay. Actually, let me just ask GPT. I think they'll explain it better. Let's search GPT. Waitlist was closed. It said I was in. Oh, if it gives it to me in Python, I'm gonna. Please don't give me in Python. Python, of course, of course. Mm-hmm. New nums. DP table, we go length. Oh, it is the left pointer, then the right pointer. Okay. What the heck? Left I minus 1. TP left I minus 1. Oh my gosh, I don't need this whole explanation. Okay. I get this. We need that to add the boundaries. Let's see. Bursting balloons between left and right, inclusive. That makes sense. We iterate over all the possible subarrays. Maximum coins obtained by bursting all the balloons is stored at. And then what does it look like? So it'll always be here. What's the point of having these values? So I understand everything up to here. Yeah, see, n minus length. Plus 1? Is it because length is 0 indexed? Why do we plus 1? I think it's n plus 1 minus length. Actually, would that mess with it? Because the only reason I think we add plus 1 is because n is nums.length is 0 indexed. We don't want the length to be 0 indexed, so the length of this array would be 3 minus 1 plus 1. Yeah, I think that's why. We'll see. Then why do we subtract 1 here? Left plus length minus 1. That's so weird. Okay, so this is just like the other solution. new nums plus 1, something like that. Why do we have to do this part? Yeah, why do we have to do this? To add the sub-problems? So 3185. Yep. 1 times 3. 3. Still on length 1. That's smart. That's smart. So oh, I see. But what is so? This is row, this is column. So we do column minus 1, row plus 1, column minus 1, column minus 1, row plus 1. Okay. Oh, that's smart. How does it know? 1630. So at the end, we just take this, max this, max this, max this. So weird. Three bullets in the array. So this is calculating not the last, this is calculating the first. Which first pop would lead to the most? 315. Is 315 in there? 315. It is there. This isn't bursting 3 last, this is bursting 3 first. Isn't it? Because if it was last, it would be it would multiply 3 times 1 times 1. TP0, TP1, 2. Show me the happy path. Maybe that'll. Bro, what kind of explanation is this? That didn't help. Yeah, this. Okay. I'm spending too much time on this, so I think. Nice to have. Yeah. Backlog, that's what we'll do. Okay. Solution first balloons. DFS is quite intuitive, however, the tabulation method is not as clear. It would be worthwhile to look into with extra time. Okay. I think I should do this at the end of the day because I just did this like 12 hours ago or 14 hours ago. Yeah, I don't want to, I already know like most of this anyways. Okay, so we'll do this at the end. Time of space complexity. Okay, this is gonna be interesting. Generate parentheses. This one's pretty easy. I don't know the time complexity for it though. That's why. I think Leetcode has a time complexity video. Courses, lessons. Yeah. How long is this thing? Like 20 minutes. Okay. I might just watch that. Because I forgot everything from data structures and algorithms. Well, I forgot the time complexity portion and the space complexity portion, to be honest. Okay. Cool. All right. Yeah. Okay, I'm gonna go to the bathroom. Okay, let's see what happens here.
Hey everyone. Hey everyone.
Oof, that's pretty loud. Let's try this.
Welcome back, and let's write. That's pretty loud.
Okay.
Some more Leetcode today. So today I want to run through all the common big O runtime complexities that you'll need for coding interviews. And by the way, all of the code from this video will be available for free on leetcode.io. If you're not familiar with it, it's basically a site that I created. It's got a ton of free content to help you prepare for coding interviews, including code in Python, JavaScript, Java, and C++. And I've also started making courses. So far, I completed the Data Structures and Algorithms for Beginners course and the Advanced Algorithms course, and I just started uploading the System Design for Beginners. Light is big of this to all current and future courses. So first of all, what even is big O time complexity? Well, it's basically a way of analyzing the runtime, the amount of time it takes for our algorithm to execute as the input size of our algorithm grows. Typically, we can expect as the input size of our algorithm grows, the execution time of the algorithm is also going to grow, but it could grow linearly, which, this is a function you might be familiar with. We're used to y equals x. In terms of big O, this is represented as big O of n, where n is just a single variable. That's our x-axis. Now, this is where we take a different turn from algebra. You could have another function like this, which is, for example, n divided by 2, but we actually don't care about the differences when those differences are constant values. We only care about the variable here, which is n. We don't care about the divided by 2. And that's true for all big O runtimes. We also don't care if, we have n plus some constant like 5. Like that might look something like this on our chart. It just starts at a different spot and has the same exact slope, but we don't care about these constants either. So the first runtime we're going to look at is big O of 1. I know we said that we don't care about constants, but in this case, 1 is a special constant that we do care about. And as you can tell from the chart, no matter how much our input size grows, the time complexity of big O of 1 time algorithms is always the same. You can see it's a flat line because the time it takes for these algorithms does not change based on the input size. These are the most efficient algorithms. So for example, if you have an array of values like this, it's a constant time operation to add to the end. It's also a constant time operation to remove from the end, or just to search an arbitrary index, just to look up a value at any index, whether it's at 0 or 1 or 2. And the same is true typically for a hash map. So to insert any value into a hash map is constant time. To look up a key from a hash map is also constant time. And to remove a key from a hash map is also a constant time operation, and the same operations could be applied to hash sets as well. We also have big O of n, which, as we discussed, is the linear growth scenario. So as our input size grows, our time is going to grow proportionately. So if we're given some array of values and we want to take the sum of all of those values, this sum function is going to be a linear time algorithm, because we're going to have to go through every single number in the array. So with just 3 values, it won't be too bad. But as our input size grows, so if our array had 1,000,000 values in it, so then the runtime of calculating the sum would also grow. And of course we know that's going to happen because under the hood we're going to have to loop through all of the elements. So looping through a list of elements is also a linear time algorithm. Inserting in the middle of an array and removing from the middle of an array is also big O of n. And that's because when we talk about big O of n, we mean the worst case runtime. Because in some cases, like inserting in the middle, well, for example, inserting in the middle of this array could be over here, in which case we would have to, put a value. Let's say we're inserting the value 100. We'd put 100 over here and then move the 3 into the next position, and then this would be our new array. So in this case, we only had to move a single value. But what about if we wanted to insert the 100 over here? Then we would have to insert the 100 here. We'd have to move the 1 to the right. We have to move the 2 to the right, and we'd have to move the 3 to the right, so that this would be our new array. And in this example, we had to move every single value in the array. We know that's an n time operation. So since we don't know where we might insert in the middle, we take the worst possible case, which would be big O of n in this case. Also, removing from the middle is going to be similar. If we remove from the end, it's a constant time operation. But if we move from an arbitrary position, for example, the first position, then we would have to shift every other value to the left, and we'd end up with an array that looks like this. Now, searching an array is also a linear time algorithm. In the worst case, we would have to look at every single element in the array before we realize that the element, in this case, if we're looking for 100, doesn't exist. It didn't exist anywhere, and we had to look through the entire array to figure that out. Or we might find the element. We might even find it in the first position, but we take the worst case, which is going to be big O of n. Another one that I get a lot of questions about, if you have a set of values, in this case a list of values 1, 2, 3, and you want to heapify them, you want to build a heap out of those elements, the heapify algorithm actually runs in big O of n time. If you don't have to individually push an element to a heap, it runs more efficiently. If you can just build it from
But I
scratch,
don't
this
remember what a
is
heap
time
is.
operation. A couple more common algorithms, the sliding window algorithm also runs in linear time. And I'm actually going to quickly go on Leetcode.io over to the sliding window section. And the second problem in the list, when you take a look at the code, you see that it does have nested loops. But that doesn't
It's O of n, because it's O of 2n, and then you remove the non-dominant constant.
Complexity is n squared, but that's not always the case. The same is true for the monotonic stack algorithm. So once again, going on Leetcode.io,
because you go through everything at most twice, so it doesn't grow linearly.
It also has nested loops, but this algorithm actually
O of n.
O of n time. If you want more details on these problems, I recommend going to Leetcode.io. You can check out the video explanation, and I go more in depth to analyze the time complexity in each of these videos.
Is that what daily temperatures is a monotonic stack problem?
When you have nested loops, the simplest case is if you actually have
O of n squared.
array and you wanted to iterate over that array, you would need nested loops to do that. So for example, if we had a grid like this, 3 by 3, so you know it's squared, so this could be any arbitrary dimension, though n by n, you want to first go through every row in this grid, and then for every row you want to go through every single position in the grid. So the outer loop is going to go through every single row, and the inner loop is going to go through every position in each individual row. And what's the size of this grid? Well, it's going to be n squared. That's how we get the big O time complexity for that. This is pretty simple. Another case that kind of trips up some beginners is if you just have a single array and you want to iterate through it n times. So if you have an array that looks like this, of size n, you go through it once, that means the big O time complexity is going to be n. If you go through it twice, the time complexity is going to be 2 times n, which we know reduces
to
just
n.
big O of n. But what what if you iterate through this array n times? Well, then the time complexity is going to be n times n, which would be
n squared.
But it's actually not very common that you iterate.
Yeah, why the heck would you do that?
N times. What's more common is
two-dimensional arrays.
Through the entire array once, and then you iterate through every element in the array.
Oh, or that. Yeah.
And then you iterate through every element except the first two positions, and you keep doing this until you've just iterated.
That's still O of n squared, though,
so
I think.
This is a diagram of doing that. You go through 4, 3, 2, and then 1. So what would be the time complexity of doing this? Well, mathematically, this is actually a well-known series, and it can be proven that this will roughly equal n squared
There you go.
by 2. But if you're not smart enough or care about that math portion, an easier way to identify that would be, well, here we have a square, right? We have an n by n squared. Now, what does this portion of the square look like to you?
-1.
To me, it looks like half of a square. It basically looks like we cut this in half.
Oh, yeah.
So now you're
That's a good way of thinking about it.
Iterating through an array like this is going to lead us to n squared divided by 2 time complexity. And like I said,
That's a really good way of thinking about it.
So this 2 does not matter.
Yep.
Therefore, we say that iterating through an array like this is also n squared. A lot of people kind of rush over this, and I'm pretty sure most people never actually learn this or care about it, but that's okay because you don't really need to anyway. But now you know something.
Yeah, I can't think of many problems that have that.
About how inserting into the middle of an array is an n time operation. So
Yep.
insertion sort, which basically inserts into the middle of an array n times, is going to have
N squared.
time complexity as
Okay.
well. Another one that's pretty similar to n squared, so I won't actually draw this one out on the grid, but n times m. This could mean a two-dimensional matrix that's not necessarily a square. So
Yep.
in our example on the left over here, we could have some rectangular array that looks like this, where we have 2 rows and we have 3 columns. So in this case, n might be the number of rows, where m might be the number of columns. We actually have 2 variables this time, which is perfectly valid in big O notation. Now, if we can have n squared, why stop there? We can also go up to
N
We
cubed.
could actually go higher and higher to n to
And
the power of 4, to the power of 5, etc., but I won't
then
do
it's
that.
n, or no,
To even have n cubed.
2 to the n and then n factorial.
This is usually the highest that we get to. Usually you don't have algorithms that go up to n to the power of 4, but it's possible. And I think you would be able to identify that case if you're able to identify these as well.
Yeah,
Of
you
course,
should.
have some kind of three-dimensional data structure. More commonly, though, you'll just have a single array, and you'll want to get every unique triplet from that array, for example.
Bruh.
So in this case, we would need 3 nested loops to iterate through every single triplet from this input array. Now let's move on to some of the more complicated ones like log n. This is
Binary
where we get
search.
more math involved, and I bet you most people don't know how to analyze log n time complexity. They kind of just memorize it because usually log n is applied to binary search.
There you
For
go.
example, on an array, or you could run binary search on a binary search
Tree.
These are the 2 most common algorithms, but there's also pushing and popping from a heap, which is another common one. On an array, the reason binary search runs in log n time is because
you have the
every
array
iteration
size
of
as you
loop,
go.
We eliminate half of the elements from like consideration. We don't need to search this half elements, for example. So then we'd be left with 2 elements, and we could keep cutting this array basically in half until we have nothing remaining. That's when we would have completed our binary search. So the question is, given an array of size n, how many times can you cut the value n by 2? How many times can you divide it by 2 until it equals 1?
You can divide it
another way of
n
talking about
times.
this would be, how many times can you take the value 1 and multiply it by 2 until it's equal to n, aka 2 to the power of what, x in this case, is equal to n. How do we solve this mathematically?
Then you get the
By
log.
definition, that's what log actually is.
Yes.
We take the log of both sides, and then we realize that x is equal to log n. So
N.
therefore, the number of times you can take an array like this and divide it by 2 is equal to log n. In this case, the base of our logarithm is going to be 2. So that's where this comes from, and the idea is the same when you're talking about binary search trees, at least if your BST is balanced, because as we search it, we're either going to go to the left or to the right looking for some target value. So if we end up going to the right, that
You
means
eliminate
we
half.
eliminated the entire left half.
Given
of the
that it's
tree
balanced, though, I
and
think.
we do this recursively, So we start with a tree of size n, and we basically remove half of the elements from consideration until we find the target that we're looking for. That's why this is also a log n time algorithm. So log n grows pretty slowly. You can't tell from this chart, but actually for really, really large input sizes, log n is practically a flat line. Like, the difference between log n and big O of n is massive. I think log base 2 of 4 billion would be something like 32. So even with an input of billions, we get a very small 2-digit number. Now we also have n multiplied by log n. And this is actually only marginally less efficient than big O of n. It's a lot more efficient than n squared, just like how log n is much more efficient than big O of n. The most common algorithms for n log n are...
Wait. I was going to say, like, there are problems that you need to sort the input array, then process.
For example, merge sort, and we usually assume that most built-in sorting functions
are
n
log n.
So if you need to run the built-in function in a coding interview, you can basically assume that it's an n log n algorithm. Heap sort has the same runtime, and this kind of illustrates how we can get a runtime like this. We know that popping from a heap is a log n time operation, and if we have a heap, of size n, and we have to pop from that heap while that heap is non-empty, then we end up doing n operations, which take log n each. Therefore, we get n log n.
Wait, what? Oh, because we're heap popping n times. Okay.
So, now, in this example, before we started running the heap sort algorithm, we actually had to build the heap. So this took big O of n times. So actually, the overall runtime was
n plus n log n. But n log n is bigger.
On our chart, well, with big O notation, we
because n plus n is basically 2n.
If we have a term like this, which is strictly larger than this term, we don't care about the smaller term. But we can have a time complexity where we have m plus n log n, and in this case, since m is a different variable from any of the variables we have here, we don't know that this is strictly smaller than this one, so we have to include both of these in the big O time complexity, but we don't have that in this case, so we reduce the time complexity to just be n log n. Now let's get into some of the non-polynomial runtimes, which, starting with, the most common is 2 to the power of n. And this is the part where I can start going on a nerd tangent and talking about how this equation is actually just a reflection of the log n over, this axis. But I'm pretty sure nobody cares about that, so I won't get into it. But feel free to comment if you're interested in the math stuff. It's most common to have a runtime like this when you're talking about recursion. So this is an example of 2-branch recursion, where our recursive tree will have a height of n, but we'll have 2 branches every time. So this is recursively calling some recursive function. It's not really doing anything, but here you can see we have 2 branches of recursion. Visually, it would look something like this, similar to a binary tree, but in this case, the height of this tree would be measured in terms of n. So for example, if we were given some input array of size n, and we wanted to get all possible combinations, that would be one example of 2 to the power of n runtime. So for example, computing the Fibonacci sequence recursively is a pretty common example, or combinations. Now, if we can have 2 to the power of n, can't we have 3 to the power of n? And what about 4 to the power of n? Yeah, you can have pretty much any constant, let's call it c, raised to a power of n. Now, I'm not going to...
It's determined by the number of subproblems?
Base value, we will have, increased runtime complexity. So an example of that would be pretty similar to our previous recursive example, but in this case...
What the heck?
We have an arbitrary number of branches, so we use a loop to do that. So in this case, our constant c is going to tell us how many times we need to loop and make a recursive path. So in this case, if c was 3, we'd
c to the n
tree with 3 branches, and the height of the tree would continue to be n, so we would end up with a time complexity of 3 to the power of n. Now, how am I getting that time complexity from a decision tree? Well, think about it this way. If we have 3, branches on the first level, we have 3 values here. Now, for each of those, we're going to have 3 more branches, and then for each of those, we're going to have 3 more branches. We're basically going to keep doing this until we reach the entire height of the tree, which in this case is n. So we're basically going to have a number, our base value, 3, multiplied by 3 and just keep multiplying it until we have n of these. Therefore, we get 3 to the power of n. Now, a pretty rare runtime complexity is the square root of n. You rarely see this, but I still think it's worth mentioning. You will rarely ever see this in a coding interview, but I think it's still worth mentioning. The only example I think I've ever needed this for is getting all the factors of some value. So for example, if we're given a value n and we want to get all the factors of it, we will go through every value between 1 and the square root of n and check if any of those values is a factor of n. And since this could possibly produce some duplicate factors, we add those factors to a hash set, which we know is a constant time operation. So the number of times this loop is going to execute is of course going to be the square root of n. Now I won't go super in depth on why this algorithm works. If you want to know, feel free to ask in the comments. It's really more of a math problem than a coding problem. And lastly, we have
factorial,
which is a math equation, which basically means, you know, if we had 5 factorial, that is 5
times 4 times 3 times 2 times 1
times 2 times 1. So basically it ends up being a very big number. We say that this is bigger than 2 to the power of n, because 2 to the power of 5 in this case would be 2 times 2 times 2, 5 times, and you can see that just by looking at these two, since factorial has the potential for having larger terms than just some constant value 2 or 3 or 4, that this is going to grow much quicker than this one. Now n factorial is pretty rare. It mainly comes up for permutations and sometimes in graph problems, for example the traveling salesman problem. But I think you don't have to focus too much on n factorial. You mainly have to know that it's very inefficient. So if your solution is n factorial, most likely you don't have the optimal solution. But sometimes n factorial is the best you can do. In a real interview, I don't think it would matter too much if you can, precisely tell, is your algorithm n factorial or is it exponential to the power of n? It wouldn't matter a lot. And also knowing the exact difference, for example, the square root of n is actually growing quicker than log n. You could kind of figure that out just by doing some math in your head. Like I said, the log of 4 billion is going to be something like 32, whereas the square root of 4 billion is still going to be a very large number. But this is mainly to give you a high-level overview of how these time complexities relate to each other, because that's what's important. You need to be able to know how efficient your algorithm is. If you see your algorithm is factorial or exponential or even n cubed,
you're cooked.
It's not super efficient. You want your algorithms to be on the right side of this chart, though sometimes it's not.
Wait, that's the video?
If you found this video helpful,
Bruh, I knew all that already.
a lot. If you're preparing for coding,
I thought he was gonna go into bro. I thought he was gonna go into like how to calculate it and stuff like that. Oh my goodness. Well, that was a good refresher anyways. That's interesting. That's a bit upsetting. Okay. Okay. So we need to figure out a better way to learn all this stuff. Okay. All of these need to be moved up one before this because, yeah. Space attack Alexi. Recursion graphs and backtracking. I need to go bathroom again. Okay. See, if I do this, I have to do backtracking, and I hate backtracking. Like this stuff scares me. Okay. Well, we gotta do it, so. Okay. Let's delete this. Time complexity of recursive function depends on how many times the function is called and the work done at each level of recursion. Consider the Fibonacci sequence. So here, the function is called twice. Fib n results in 2 more calls, except for the base cases, creating binary tree function calls. A binary tree of function calls. Oh, that actually makes sense. So you have n, 2, 2, it just keeps on splitting n times. Space complexity recursion is mainly about the stack space used by recursive calls. Fib, space complexity is O of n because the maximum depth of the recursion tree is n. And the number of nodes and edges. For DFS, the time complexity is O of V and E. DFS. Graph node visited. Okay. For neighbor and graph. Okay, so this is just a graph traversal. Each vertex and edge. Okay. Space complexity for graph algorithms can include the space needed for the graph representation, like adjacency lists and the stack in recursive DFS. What? Oh, the call stack? The recursion stack. Because at worst case, is the recursion stack the number of edges or the number of vertexes? I think it is. Because if we just do a traversal, it will call this until it reaches the furthest node from the root. Oh, that hurt. Backtracking. Time complexity is O of n factorial because the worst. Why are you giving me n queens to? So backtracking, think about the depth of the recursion and the number of possibilities being explored. Try calculating the complexity of recursive problems like factorial and merge sort. Graphs. Analyze BFS and DFS on different types of graphs. Sudoku, the n queens problem. This kind of helps. Recursion. What the heck? Oh shoot. This isn't plugged in. There we go. Okay, to be honest, I think the best way to learn and practice the time complexity is just doing the problems and figuring it out. And then when I get stuck, I just need to walk through exactly why. Yeah. Okay, cool. So now that that's done, let's just go through all the backtracking problems and understand them as extensively as we can. Yeah. Okay, cool. subsets. Why did I delete that? I'm so dumb. Okay. So, what's the time complexity of this? I have no clue. Space complexity probably O of n times m. It's a two-dimensional open array, so yeah. Mm-hmm. Is that actually how it works? How do I erase? Okay. Nope. Cool. Is that actually how it works? So we have node, what is it? Okay. So we have node n, we have two paths. Oh my gosh, that was awful. It's way easier to do it like this. Actually, wait. Okay, let's look at our sub problems. So we have array of 1, 2, and 3. So, oh my gosh, I need to get used to this. Array of 1, 2, and 3. 1, 1, 2, 3. Okay. So we have nothing. So we have null, null, include 1 or not include 1. So we have 1, nothing. Include 2 or not include 2. Right here. 1, 2, 1. So how does this avoid duplicates? 2, two subproblems. 1, 3. 1, 3. 2, 3. 2, 3. Trackpad and mouse. Terrible legibility. 2. Oh my gosh. 2 and then 3. Yeah, how does it avoid this path? That's my question. It's 1, 2. 2 and then 3. 2, 1. 1. So how are we avoiding? It's a terrible tree. How are we avoiding the duplicates? Oh, we're avoiding the duplicates because we always iterate by 1. So if we okay, so if we go back, this is root, so we have the root, and it's 1 and 2. My gosh. 1 and 2. So it's 1. And then we don't include that. And this is I equals 1. Or 0, sorry. So when we keep on drawing this out, it's either we include or not include 1. So when we're here, we have 1, 2. Oh, do we not even give it the option? Yeah, we don't. So I'm definitely thinking about this wrong. Okay. Time to rethink this through. Okay, so we have tree here. We're on index 0. So we add 1. And then we backtrack again. And then we're on index 1. So then we add 2. Add 2. Okay. And then we go down another one. And then we add 3. So we have 1, 2, and then 3. Now what happens under this subchild? Because there are 2 subproblems. So then we remove 2 and then add 3. 1, 3. Now this is done. Then here we remove 1 and add 2. Okay, so that's how it works. And then here we have 2 subproblems where we add 3, 2, and then 3, and then here we remove 2 and then add 3. So then what happens in this? Because we add 1, remove 1, add 2, remove 2, add 3. So then here we add 1, and we remove the last one, which is nothing. what's happening in, so we enter backtrack in the first iteration, and that gets us index 0. So we add 1 here, we go through that path, we remove this one, and then we go through the next path. So we still have index is now 1, and then we add 2, remove 2, does that happen in this path? How is it avoiding duplicates? Let's have GPT write the tree out then. Can you write the tree out? How does it avoid this duplicate though? Oh, I've been thinking about this wrong the whole time. Okay. Because we only add, okay, that makes sense. Because we only add to the output array when we're at the end. So now we need, let's rewrite this. Oops. So we have the root. We're at, oh my gosh, what the heck? We have the root, and then we have 2 paths. We add 1, 2 more paths. We add nothing here. It's not wide enough. Jeez, that's large. 1. Here's 1, 2. 1, 2. And then 2. And here. We have 1, 2, 3. 2, 3. Okay. And then here. Actually, why did they add 1 in this path? Shouldn't this be 2? Because, so we add 1. I think it's because, is this tree any different? Yeah, slightly different structure. Oh, who writes it like this, bro? What the heck? What are you doing? Can you re-visualize that tree? Re-visualize the tree. There we go. Oh my gosh. We have to delete, don't we? Okay, I think this is doing it wrong. Let's not worry about it. Delete 2 and then add 3. So 1, 3. And then here is add 3. 1, or no, 2, 3. Here. 2, 3. And then it's just 3 here. So all of these are added. And then on this side, it's nothing. To exclude. Let's see. This is where my tree fails. 2, 3, 3, blank, 3. What am I doing wrong? Oh, I'm thinking about the removals wrong. Okay. So let's go here. Okay. So it's 1. 1, and then 1, 2. 2, and then this is 1, and then this is 1, 2, 3, 2, geez, 3, and then 1, 2, 3, and then 1, 2, 2. And then here, 1, 3, 1, 2, 2, 3. 2, 3, 2, 3, and then here it's just 2, and then this path is gonna be 3, and this is blank. Okay. So 1, 2, 3, 1, 2, 1, 3, 1, 2, 3. Ooh. No, it's 1, 2, 3, 1, 2, 1, 3, 1, and then 2, 3, 2, 3, blank. Oh, jeez. Okay. That's pretty straightforward now, actually. Oh, wait, actually? Why'd I get rid of it? Please tell me you have my history. No, never mind. Okay, so if we look at this tree, the reason why it's 2 to the n is because there are 2 paths for each height of the tree. It's because we have 2 subproblems. 1, 2. So we have subproblems here. So we multiply by 2. And then we divide by n, right? Dude, why is it showing a piecewise function? Dude, I wish I never forgot this. Okay, at least we know how it works. Time complexity and space complexity. It's easy to justify it because you can just think about it, I guess. Yeah, so combination sum. Oh, index, not length. Hmm. Something like that, because we're not returning, we're not exiting if the base case, or if we've had too big of a combination. So we needed that base case. Okay, cool. You know that subset thing actually. Whiteboard. You know, drawing out the tree actually helps a lot. Who knew? Okay. Oh my gosh, my back. Okay, so, jeez. So if we draw, oh jeez, zoom out a little bit. If we draw the tree, this is the root. What's our use case? Okay, I need to write these out. So we have an array of 2, 3, what else? 2, 3, 6, 7. So we have an array 2, 3, 6. 6, 6, 7, and our target is 7. Oh my gosh. Okay. So if we're here, we have our 2 paths. We're going to add 2, add 2, add 2. Okay, add 2. Now we're at 6. And then this is going to break. Actually, let's just do the happy paths. Yeah, so we add 2 here, 2 here, 2 here, and then this path will break. So we'll go here, and then we add 3, and then we've hit 7. So this is a good path. Two, 2, 3. Is that the only path? It's 2, 2, 3, and 7. 2, 2, 3, 2, 2, 2 is not gonna work. 3. Oh, 3, 2, 2 would work, but are we adding? Yeah, we're not adding duplicates. So how do we avoid that actually? Unique combinations that sum of 2. Okay. Yeah, how do we avoid the duplicates? Because now it's going to be 3, 2, oh, we're only going forwards. That's how. So yeah, and then it's just 7. This is a terrible example. Give me a better example. Okay, 3, 3, 5. And then what's our target? Okay. That was terrible. What? 3, 3, 5. So we have this. What's our target? Target's 8. Target is 8. That's what we're looking for. How do people do this? Okay, so we have a root. We'll include 3. Wait. Is it? 7. It's 2, 3, 5, not 3, 3, 5. I was gonna say, there are not that many combinations for 2, 3, 5. 2. So we avoid duplicates by only going forwards. Is it given that the array will be sorted? Because I feel like this only works if the input array is sorted. And that they're unique, which it says right here. Unique, are they unique? Yeah, distinct. What's the difference between distinct and unique? I feel like that's important to know too. Okay, so 3, we'll get rid of that. So we have 2, 2. I'm gonna really focus on legibility here. 2, 2, 2. So that's That's good. Three. 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 That's good. Three. Every path for 3 is not going to work, so then it goes to 5. And then it says we're good. So this doesn't work. 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 And then anything with 5 doesn't work. Cool. Yeah, that makes sense. Time and space complexity, no clue. No clue. I'm going to say it's for each sub-problem. This might be n factorial. Because for each sub-problem, we have up to the length of the array. Yeah, I wonder what the... What is the time and space complexity for combination sum? It does prune bad leaves. That's crazy. I wonder what Leetcode says the time complexity is. Oh, he doesn't even write it. It's 2 to the power of t. Okay, so it's the same reason why the time complexity for subsets is true, man. So I assume the space complexity is the same. But what's space complexity? Nico doesn't even go into space complexity. Let's look at the solutions. Simply check all combinations. They don't even, what's K? Like, what does K represent here? Oh, what is... You didn't explain time complexity, bro. Like, that makes no sense. What about the call stack? Like, that's just actual space complexity. Oh, it doesn't do that because it prunes. How you spell? That's kind of dumb. I didn't even think about that. Oops. Does the combination sum problem assume a sorted input array? Why not? So how does it work without a so then how does combination sum avoid duplicates? Oh, it avoids duplicates because all values are unique. Oh, does combination sum avoid duplicates because all values are unique? Input array 2, 3, 6, 7. 2, 2, 3, 3. Okay, so I think if we go back to this, combination sum is able to avoid it because it only moves forward in the array. I think. Does this implementation only remove duplicates by only moving forwards within the array? Okay, that's smart, that's smart. Permutations now. Oh my gosh, bro. I think we need a visited array. Track nums visited new array host output. No, we don't need index return output. Public int do backtrack and nums boolean. This looks so ugly, I'm redoing it. We need to add the permutation and then call backtrack. I don't think we need, yeah, we don't need two subproblems here. There's no point because because we're looping through 0 through n. So we're going to hit duplicates anyways, so there's no point. Wow. Wow. Did not expect that. Wow. That's crazy. Yeah. So you need... I wonder what the tree looks like for this. What was it? 1, 2, 3? Yeah. 1. 1, 2. 1, 2, 3. Mm-hmm. Oh my gosh. I drew the exact output. I just realized my head's covering this. Wow. That's a lot easier than I thought. each path has 2, so this is the same thing, 2 to the power of n. Yeah, each path has that. What is the space and time complexity for permutations? For the permutations problem. It's n factorial. Oh, it's because we're looping, I think. Leetcode also said permutations is generally factorial anyways. Yeah, I wonder how important space complexity is. Like in the real world. Okay. N factorial. Okay. So the reasons why we have to order, the reason why we have to order is because we want to avoid the duplicates. Same thing. Index. Yeah. Whoa. But that's not right. There we go. Next. Subset. Yes. Oh yeah, so, that's, okay, I don't need the second sub problem because I'm looping. See, I never got that before. I never understood that before. Unless I get this wrong. Okay, what am I doing wrong? So, I deleted the if statement, and I have no clue why I deleted it. I just had like a hunch that it would work. Okay, let's see. Yeah, so SSGPT. Why doesn't this work? It just told me that I did it wrong for the completely wrong reason. So we're just gonna have to figure it out ourselves. Okay. 1, 2, 2, let's do that. So we have the 1, 2, 2 array. 1, 2, 2, 2. Okay. Yeah, so then we have a root. we're gonna add this right here. And then when we get 1, you add 1, call it, and then add this. So we're gonna, sorry, I'm gonna put it right here. 1, add this. And then once it gets to 1, we're adding 2. And it's gonna add this. And then it's gonna go down this path and realize we have, oh no, it's not. So it's gonna be 1, 2, so big, 1, 2, 2, oh my gosh, 2, 2, and then it's gonna add this. So then what do we do? So then it's gonna go back. Well, it's gonna go here and then we exit, we remove 2, and then try to backtrack again. No, so this leaf is done. 1, 2, we go back. And then we're gonna hit a duplicate here. So this is, we've hit the indexes, so both of these subproblems are done. And then here, we hit a duplicate in the loop, so this is done. And then here, move that. And then we hit a duplicate in the loop, so we remove that. So it's gonna be 1, 2, 2, 1, 2, 1. Is that the answer? Oh, 2. Whoops. So then, yeah, then it's gonna add 2 here. We're gonna go down this path. And what are we gonna add? 2. And the only reason why this passes is because 2 satisfies this condition. Yeah. And then we've hit the end of the indexes, so this path is done, this path is done. Wait, it's not really like these have 2 paths, to be honest. So we can get rid of this actually. And this. I'm gonna put this back. So we have these 2 problems. 1, 2, yeah. And then here, it exits because it's a duplicate. Okay. And that only works if we sort the array. Okay, that makes sense. Subsets. Time complexity, no freaking clue. We only have 1. Like, let's undo this. Space complex, I'm not even worrying about space complexity. So this will run, we backtrack O of n times. This occurs in n log n, so that's important. It's definitely not faster than n log n though, or slower than n log n, or yeah, faster than n log n. N times n squared? Potentially. Let's see. Handling duplicates over time complexity. Sorting takes all of. Oh my gosh. The worst case time complexity is still O of n times 2n. Are you sure? I'm gonna stop asking the generic ones. I just need to. What's the problem? What is the time and space complexity of this? N log n times 2n. Where's the n come from? Oh. Okay. It's all n times 2n. Fascinating. I really don't. I don't really understand that. Okay, combination sum should be around the same. So they're all, most backtracking problems are just going to be 2n, 2 to the n. So we have to sort the array here. List integer output. candidates, not combination. Yeah, this one's pretty straightforward. Now it's all pretty straightforward. I don't get like how to calculate time complexity for this. Like I wouldn't be like, if I just throw this in, it's probably time of 2 to the n and space 2 to the n. Yeah, because you either include or not include the... Okay, actually, maybe I'm just being dumb about this. Cool. Yep. 2 to the n, space. 2 to the n. Okay. So most of this, I can just, as long as they're 2 sub-problems, yeah, we're chilling. And then this should be a graph problem. I don't know why it isn't a graph problem. But this is cake. I say that, I'm not gonna know it. Oh my gosh. Oh, I forgot the visited. So if we visited this tile, false. All is true, and then if index equals board call. No. It's before we do the check for this, if the index equals the length of the word, we can return true. Yeah. And then this is where we do the DFS. So if this or dot char at index does not equal word row call, and return false, visited equals true, and then I need to sandwich that, so visited row call is false, and then DFS. Wait, what do I have to do? Okay. Visited index plus 1. Is this right? I think this is right. True, false. Oh my gosh. What am I missing? What am I missing? It's always returning false. I'm iterating on the index, so we should have the right exit conditions. Visited row call. Visit equals true. Visited word. Index plus 1. Index is going to be 0. Yeah, so we go up, down, left, right. What the heck? What am I doing wrong? A. Visited row call. That is right. If we visited already, or if the word isn't what we're looking for, we return false. Oh, it's if. Oh, geez. Okay, we gotta restart this. So if this one call, word visited, word index plus 1, or yeah. There we go. Beautiful. Beautiful. O of n times O of n times m, where n is the number of rows, m is the number of columns. That's this, and then d of s is O of m times m. Space. Space, we needed O of n times m extra space right here. And in terms of the call stack, I actually have no clue. Space and complexity. There it is. Oh, nice. I got it right. Cool. This is just DFS. I don't know why this is in backtracking. I guess because you backtrack when you don't find the right thing, but you do that with most of DFS anyways. Palindrome partitioning. Oh, bro. This is annoying. This is a graph or backtracking probe? That's interesting. We're actually very close to finishing. Generate parentheses. What problem is that? Isn't that like stack? Yeah, it is. But I just use backtracking for it. Greedy. Intervals. Advanced graphs. I don't think I know how to solve these. But once I refamiliarize myself with like prims and Bellman-Ford, then this will be cake. Yeah, I brushed up on most of this. Bit manipulation. This is one of those things where it's like once you learn it, it'll be fine. I just don't know it. And then this is just math. Huh. Interesting. Okay. Give it a string. I know you have to like What? String? So, string. Mm-hmm. How do I add the digits to it? Yeah, how do I grab that? Because the problem I'm having is we need to be able to abstract on for each digit and each letter and each digit. But right now I'm only on the digit layer. And I need to be on the letter layer. How do I? Yeah, I don't know. Oh. Okay, that was right. Well, I knew that was right. Okay. What's this? Index. Why do we need an index? Interesting. Zero. We don't even need to do that. Yeah. Same thing. Not just combination. Yeah, I don't think that works. Interesting. Oh, wait, I totally get it. It's literally just permuting. Okay, so this is O of 2n too, because it has a choice to add or remove. Or, no, it's O of whatever the average of all of these is. So it's like around 3n. Yeah, I think. Letter combinations of a phone number. Actually, before I check that, I want to check space complexity. O of n for each O of O of n, where n is the number of letter combinations. It's actually the length of O of n, where n is the length of digits, times m, where m is the number of combinations. Or not. Or not. Wow. Oh, yeah, so I was right. Time complexity is 4. So they just take the average, or the worst. Because I said it was 3n, or like just above 3n. Yeah, that makes sense actually. Okay. Is the length? Yeah, it's length. Cool. String builder. You gotta get that string builder. I'm sure I could do it actually. It's new string builder. I knew it. I knew the faster one's gonna be string builder. Combination. Two string. Oh no, it's new string. Something like that, and then combination dot append letters dot char at I, and then combination dot remove. Oh, what's the? Is it like delete char? String builder. Remove. Is it remove last? String builder, delete. It's like delete char at. Oh, it's literally delete char at. Okay. So we go here, deletes char at combination. This should be the fastest. There we go. Okay, I'm gonna do it one more time with the string builder this time. Public, no, it's up here. Public final string letters. You see the photo. GHI, JKL, PQRs, 2V, WXYZ, string, list, left digits. too bad, not too bad. I gotta redo that. Okay. That's not gonna work. 70% acceptance rate? That's crazy. Because I don't know it. How would you even do it? Like, I can get the palindrome. How do I partition it properly, though? Only lowercase. See, I would feel bad if I just looked at the answer right now. But I literally don't know what to do. Backtrack. I don't even know if this involves backtracking. Dude, what the heck? Oh my gosh. Given a string S such that S substring partition palindrome, return all possible palindrome partitionings of S. I don't know how to. I don't get how we're gonna partition the remainder of this. A, B. Do the length, but then how do we can loop through the lengths, but then we wouldn't be able to get to the variable lengths where we have a palindrome that's 2 and then a palindrome that's 1. So we could like do sub-problems. Like, that actually might work. We divide and conquer it rather than. So it's like track S. What? Oh, this is tricky. Backtrack 0 output. String builder. String. Output. Turn output. If this actually might need like a new list here. A string partition. Oh, that looks so ugly. List string output. String builder if partition. See, then how do we even like what are the base cases here? Because yeah, what are the base cases if we do this? Oh, it's S. Is it S? Like S dot length is 0? Output dot add new string builder dot toString. Otherwise. Now we have to do palindrome detection. How are we going to do even and odd? 0. Well, maybe we do length here. Length has to be less than S dot length. Is palindrome S length? This is so shot. S on the left and the right. All left, position right, S touch, or, yeah. Is palindrome I plus plus. Yo, what the? Is palindrome new substring. Oh, I'm so dumb. So if quotation dot add string builder dot toString and string builder dot toString. This is so wrong. Yeah, this is wrong. I'm looking at the answer. Index I. To be honest, I almost had it. It's just this inner loop that I messed up. So it's like is palindrome if is palindrome. Oh, why did I do that? If it's a palindrome, if it's a palindrome, then am I passing in an index value? No, I'm not. And I don't need to be. So this can be 0. Turn this into 0. In index is palindrome S index I. And then this probably has to be indexed, because why would we go backwards? So if it's a palindrome, then put partition.add s.substring index to I, backtrack s index I plus 1, not index plus 1. Partition output, partition.remove, partition.size minus 1. Yeah, that didn't work. Oh wait, it's because of this. If index equals s.length. Okay, what the heck did I do wrong? I0. Y0. Does that really change anything? Oh, this will handle if it's backwards. SSF string I. That's what I'm saying. Index. So this is supposed to be +1 for some reason. That's why. I have to handle that case right here. Wow. Oh my gosh. How much? Why is this so much faster? Helper. Bro, that's stupid. Let's try it one more time. Okay, so how does this, I think I know how this works. So that's what, it is dividing and conquering. I'm just confused on why we can't put index there. Like, if I do index here, will it break? Wait, what? Yeah, it won't break. Okay, so if we do that, then we can get rid of this. Because it'll never have the left pointer be less than the right pointer, and there we go. Oh my gosh. That's so much more convenient. Okay, now I have to restart it and do it with the index. But that makes sense. Basically, we check if this is a partition, then run the backtracking on the remainder of this. It isn't really backtracking though. Is that really backtracking? It's more like divide and conquer. Yeah, so we do this, and then we run it on this, on A, B. Then it'll run, it'll say A, B, and then it'll do this, and then this, and then this. And then it'll also do this. Yeah, we're fine there. Okay. Time complexity. This is O of n. Is palindrome is O of n. Space complexity is going to be O of n times m, where... Oh no, O of n squared. Like if it was just A, then yeah, it would be O of n squared. That's worst case. For an IX, for an I index, this is O of n. Then we run this, which is O of n. But do we have subproblems? Yeah, we either add, if it's a palindrome, we either add, so the happy path would be everything's A. We either add it, if it's a palindrome, or we don't go with it. So it's just 2n. Yeah, it's just 2n. So space complexity will be 2n, time complexity will be 2 to the n. Where is the time and space complexity of this? There you go. 2n. 2n. Oh, wow. This is making so much more sense now. Okay, I have to redo it. Okay. List, string, output equals new array list. Backtrack, S0, new array list. Output, return output. Output void, backtrack. String S, int index. List string, partition. List string output if s dot length if index equals s dot length or output add new array list partition else I equals index must be less than s dot length this, and then partition to add s dot substring index I plus 1. And the reason why we do plus 1 here is because when we do is palindrome, this is inclusive for the ending index, and when we do substring, it's inclusive for, or exclusive for the ending index. Yeah, and then backtrack. S I plus 1 partition output partition dot remove partition dot size minus 1, and then we need to do public boolean is palindrome string s in left in right while left is less than right if s dot char at left does not equal s dot char at right. And this one false, and then otherwise we'll iterate left and decrement right. Return true. So that should be it. Okay, cool. That's not bad. That's not bad. And I got to the fastest time complexity, which is good. 98%. Not too bad, not too bad. Okay, that's done. N queens. I actually haven't done N queens. I don't think I've ever solved that problem. I did it for school once, but I didn't care about that. Okay. Okay. Let me get water. Okay. And queens. Okay. Is there a collection stuff, Phil? Yeah. There is. So for collection stuff, Phil, no, with shouldn't be integer either. It should be char, string, string. Wait, that's not gonna work. We don't know the size of the array. Or the, yeah. Beautiful. What if we just started with this? 4 equals new string. String. Row call board. I don't even know how to validate the positioning of the queens. I can't think of how to either. Yeah, I don't know how to validate the I'm gonna have to write so much code, and it's probably just gonna be wrong anyways. How do I do this? I'm thinking like we could have a visited, or we could have a validation board, and every time we place a queen, we fill out the validation board and then check against the backtrack. See, that's the thing. Okay. A lot of people, including me, get very caught up in over-optimization. So trying to optimize rather than just solve the problem. But the only reason why I do that is because if I don't get the optimal solution, Leetcode won't even accept the solution. This is why I think they should accept unoptimal solutions, or like really unoptimal solutions. Because then there's no point in me trying for an unoptimal solution if I'm just going to get a time limit exception. Like, it's so unsatisfying to do that. Okay. Yeah, I think I'm just going to ask GPT for this one. Show me the solution to coins in Java. That's exactly what it does? Okay, maybe I should have tried it then. Maybe I'll write it. I won't even look at this anymore. Construct? Where does construct come in? Oh. Like, bruh. Why do we start at the back corner? Wait, why do we only go by a row? Okay, yeah, I'm just gonna, oh my gosh, my scroll. Oh. What the heck is this condition? Oh my gosh. Wait, what? So replacing a queen. Then we're backtracking. Okay. Okay. That's the backtracking. Okay. Do I not need to check row? Oh, I don't because row's taken care of here. Can I not? Okay. What's wrong with this? It's probably my other diagonal condition. Didn't I do that? Oh. Why? Maybe is safe. Can you write it so that it is validating from the top down rather than bottom up? Yeah, see, this is why is safe. Huh? J has to be greater than col minus rho plus I? Col minus rho. Why do you have to subtract the rho? This is no way. There's no way. Why is it doing this? Okay. Oh. Okay. Oh my gosh, that's such a dumb thing. Why? Why? Why does it have to be greater than or equal to 0? So it checks this. It checks this. And this? Why is it? It's only checking one axis. It needs to check 2. I don't get it. I really don't get this. Because if we're taking the current... I don't get that. Because this would say it checks everything from the left up, or yeah, left up. But then that would be the right up. But that doesn't make any sense. Unless I'm thinking about the rows and columns differently. Because it would be minus, 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 minus. And then minus, plus, minus, plus. Start at the current position and move upwards towards the left. Decrementing with I, and simultaneously this checks the diagonal cells above the current position. Start from the current position, move upwards to the right. Decrementing I, checks diagonal cells above the current position. Yeah. So it checks the V, like here. Why is that important though? Because shouldn't we be checking this? I feel like we should. is safe. Check column top down at first. So we check the entire column. We know the row is safe. So we know the row we currently at is safe. We know the column we're at is safe. But it only checks everything above it. What about below it? Why don't we need to check below? Why don't we need to check the diagonal values below the current position? We do not need to check the diagonal values below the current position because of how backtracking algorithm places the queens on the board. I figured it was because of that. So we're placing it from the top down. Oh, because we're placing it by row. Oh, that makes sense. So we're placing it here, we check the V, placing here, check the V, here, check the V, here, check the V, and then we check columns and rows as we go. That's a lot smarter than what I was gonna do. Wow. Oh, I see. I'm still getting it wrong though. I has to be greater than 0. J has to be less than N. So we're going up, sideways, up, side. Up, right, up, right, up, right. And then that's up, left, up, left, up, left. Okay. So if the board ij equals Q, that's one false. Oh. What am I doing wrong here? Right diagonal, right diagonal. I'm subtracting 1 from the column when I should be adding 1 from the column. Oh my gosh. Because we're going in the opposite direction, so we don't subtract like we did here. And of course. Wow. That's crazy. Solve and queen. So output array, we fill in the board. That makes sense. We backtrack. If row equals N. Okay. We add the queen. We iterate by column. So we go from row 0 to row N, column 0 to column N. Row 0 to row N, column 0 to column N. So that's why we're only checking above. And then when we hit row N, we add that. And the backtracking here checks each permutation of how to do it. Call, so we're iterating each time there. When do we iterate the row? Right here. Okay. Is safe. Okay, and then we construct by making an array list, adding. That's very smart. Taking the array of characters and converting it. Okay, let's try it. track 0 and board output. So output. Public backtrack row int n board list string output. If row equals n, then we output dot add construct. What do we want to construct? Construct the board. And we return here. And then for call equals 0, calls plus n, call plus plus. If is safe, board row call. Board row call equals queen. Backtrack row plus 1 and board output. Board row call equals period. Public void. Public boolean is safe. Char board int row int call. If check if the columns are safe, so int not equals 0 and it has to be less than. Row I plus plus. If row I call equals q. Oh, so we only need to check what's above. Let's run false. And then for int I equals row minus 1. J equals call minus 1. Row has to be greater than equals 0 and call has to be greater than equals 0. Row minus minus, call minus minus. Oh no. Minus minus, call minus minus. If I call equals q, turn false. For int I equals row minus 1. J equals call plus 1. Row has to be greater than equals 0 and call has to be less than n. I has to be greater than 0 and j has to be less than n. I minus minus j plus plus. Board I j equals q. Turn false. J return true. Public list string struct char board list string list string equals list int row and board output to add new string row. Return output. I think that's it. where's that? Oh, right here. No. Okay, well, that's not too bad, to be honest. We're getting there, guys. We're getting there. Okay. Now what? So that's all of backtracking. Oh my gosh, that took so long. Oh yeah, I'm gonna need to redo end queens. All of backtracking. Do I need to redo palindrome partitioning? No, I don't think so. Actually, probably. Redo palindrome partitioning. Ah. How do I turn this off? Okay, I got a little distracted. What next? What next? What next? Oh, I want to see generate parentheses, see if I can do it and then get the time complete. Oh my gosh. This is why we restart this stuff. See if I can do it and then see if I can get the time complexity. Oops. Okay. What the heck? Oh, I think this changes it. We're not backtracking. Okay. There we go. So when we backtrack like this, what are our options? We can add it. We add, delete, add, delete. Worst case is we do both every time. So we have the root, and we can add, and we can include open, not include open, include close, or not include close at any given time. So is it 4 to the power of n? What's the time and space complexity of this? Space, I would say, is probably the same. I mean, they generally are always the same. There we go. Okay, so I'm getting the... Nice. I'm getting the hang of it. 4n. Okay, cool. Yeah. Okay, so I would say for the most part, at least the backtracking is good on this. Tries. Did I really struggle with that? Generally need to... Space complexity, maybe, but time? I don't think so. Okay. Design and add data. Yeah, I'm curious on whether I actually struggle with this. Try. Just not try. This dot try dot add a word. This dot try dot find word. Public try. Wait, no, I don't even need to do this. This dot root equals my try node. Add a word. This dot try node equals this dot roots for entire has word length. Char cur equals word dot char at I. Try node equals if node dot contains key cur doesn't, then node dot children dot put cur new try node, and then node equals node dot children dot get cur node dot children. Here it's search, so node equals this root. Length equals length equals plus node node.children get word.char at I. If node equals null, then return false. Turn node.word. Okay, cool. Class try node. Public string word. Public maps true character. Try node. Children. Public try node. This word equals null. This dot children equals clear hash map. Oh, this is the one with, whoops, I misunderstood the pro. Okay. Oh, wait, no, that's not gonna work. Yeah, so for the word dictionary, add word has a time complexity of O of n, space complexity of O of n. Search has a time complexity of O of n times m, where n is the number of letters in the word and m is the number of children that are in, the average number of children that each letter has in that try. And then this has a space complexity of O of n. I don't know how we're supposed to describe, like, are we supposed to describe the object itself, or? Whoops. What the heck? Yeah, of n where n is time complexity of add word. Searching for a word. I said it was nm where n is the length of word, m is average number of children. Exponential number of recursive calls? Oh, I guess. Yeah, so it depends on the branching factor. Mm-hmm. See, this is what... Why say this about the try when this only applies to the try if you add words? So why isn't this time complexity add word? Like... Yeah, ignoring the space taken by the try. Like, what? The whole point of it is to add space to the try. Makes no sense. That's the thing, like... Bro. Okay, I think as long as you explain it correctly, you're fine. But like generally, like... yeah, like... this function by itself doesn't add any space complexity, but it adds space complexity to the dictionary, to the try, in turn doing so to the dictionary. So it's like... I don't know how you're supposed to explain it. Maybe I'm dumb about it. Oh. Yeah. So I don't like. I feel bad for marking this off as complete, but I'm not really sure how else I'm supposed to be doing this. Yeah, stuff like that. I just. Oh my gosh. I guess I'm gonna. I guess I'm gonna get rid of this. Oh my god. Oh my gosh. How many problems have we done so far? I think it's quite a bit, to be honest. Yeah. Surrounding trees. So backtracking, this is actually done. Cause yeah. Time complexity of graph problems actually should be easy. Because generally with those graph, at least with the ones I'm thinking about, they're like, oh, they're just O of n times n. Or of n squared, sorry. But we'll take a look at it. I'll when I do this, I'll go through the problems and then see if I get them right or wrong. Priority queue heaps. I feel like this will be easy. Complexity surrounding trees. Oh my gosh. My mind's like all messed up right now. Space. The call stack will be at worst 1, 2, 3, the height. So given that it's balanced, O of n. So time is O of n. I wonder what space is. I think it's O of n. Yeah, for balanced trees, it's O of log n. Yeah, okay. Worst case, best case. Cool. Maximum depth of binary tree. Why am I doing that? So dumb. Okay, so two subproblems. This is the same thing. Given a balanced tree, it's going to be O log n. In worst case, if it's just a linked list, then a singly linked list, then it's going to be space is going to be O of n. So O of n. Yeah, same thing. Okay, maybe I was overthinking this. The common theme has been overthinking, so yeah. Okay. So this will be the same thing. There are two subproblems. Given we have to do a traversal to find the max depth, basically. This is basically a max depth, and we make a calculation based off of max depth. So yeah. Oh. oven. Yeah, okay, cool. Wait. Yeah, this is also a max depth problem. This is just a diff depth, or diff depth. So yeah, this is going to be this is going to be the same time and space complexity. Okay. Yeah. Same tree. Oh my gosh. So I think no matter what, this doesn't have a best case of O log n, because you basically just have to, it's just an iteration. Yeah, so I think no matter what, time is going to be O of n and space is going to be O of n. Like, and it won't be O log n for space. Oh wait, no. Okay, I was wrong about that. It is log n, because the call stack will only have log n calls in it, given that it's balanced. Okay, yeah, I was wrong about that. I was thinking about it incorrectly. This is the same thing. Why is this different? N times M. Oh. Is it? No, it's just O of the larger of the two, right? Oh, I see. It is O of N times M. So you only run into this situation when you have like 3, 4, 5, 1, 2, and it's 3, 4, 5, 1, 2, and then there's another child. Or this value is different. When it's like, it's an identical tree, but it's like one off at the very bottom. Okay, that's good to know. That's good to know. That's why we're doing this, so. Yeah. There's no recursion here actually. So space will be constant and time will be O log n because it's a binary search tree. Yeah. Wait, why is, oh yeah, I guess. If it's a straight line, it's going to be, if it's a linked list, it's going to be O of n. Yeah, space is O of 1. Okay. Cool. Yeah, so with these trees, you just have to be, you have to be aware of the balancing and stuff like that. Which one do we have less common? Level order traversal. Space will be linear on this. Okay, time. This is a tree traversal, so time's going to be O of n, where n is the number of nodes in the tree. We don't have to worry about this loop because the only reason why we're doing this is to maintain the level property, but we still iterate that many times. Space is going to be, this is going to be O of n, where n is number of nodes. This is going to be the size of the big is, yeah, so it's going to be O of n. Cool. Oh my gosh, GPT. Come on. Times O of n, space O of n. Beautiful. Beautiful. This is the same thing, bro. See, this is the same problem, but I would feel bad if I skipped it just because it was a very similar problem. Cool. Okay, so this is your traditional O of n time, O of n space if it's not balanced, O log n if it is balanced. Oops. Yeah, this is going to be the same as well. We're iterating one tree. Yeah, it's going to be the same. So the reason why the is subtree one was different was because we were iterating 2 trees. So it could have been, yeah. Then we'll log in. Cool. Yeah. O of n, space is going to be O of n. O of n, O log n. Yeah. This is the same thing. Oh, yeah, that is true. Okay, so because we had an array list in the last problem, we're always going to have the, I could actually change that. You can like, yeah, we could change that. It's like, in order, or list integer list equals new array list. And we just put k there, and then in order root dot or root list return list dot get k minus 1. Yeah, like void in order tree no roots list integer list and k. Okay. If list dot size equals k, return. Or if root equals null. And in order root dot val or root dot left and list dot add root dot val. Root dot right. Yeah, I think this will prematurely stop it and then bring our space complexity down to O of n. Or O of log n. Yeah, look at that. And then we've allocated space, so. Yeah, there you go. Haha. Okay, so now I can do that. I need to go bathroom. Which one were we on? This one. Pre-order. Okay, so this is Oven. Time. This is also a traversal that's Oven. Space, we're creating n nodes. So that's Oven. This get is O1, this get is O1, this is O1. This is O of n space too, so time and space are O of n. I don't think space is O of n because of the hash map, not because of the stack calls. So space, can it be shortened like last time? No, it can't, because we're not looking for a fixed amount. So yeah, I think we're pretty good there. I may be wrong on this one though. O of n, and then space is O of n. Yeah. No, we're looking for the worst case. Oh my gosh. Okay. Okay, so yeah, this should depend on whether the tree's balanced. We're not using any extra space anywhere, just the stack call space, which should be O log of n, and we're iterating through all of them. So it should be O of n time. Yeah, I'm not worried about this one. O of n. Yep, perfect. What? We checked if it was null. Oh. Oh my gosh. Cool. String builder, this should all be O of n. Everything that happens to string builder is O of n. This traversal right here is O of log n, or O of n time space would be O of log n depending on the balancing, of course. O of n in the worst case. Deserialize. This is O of n. This is O of n. And then this is O of n time space. Yeah, so it's the traditional stuff. Space, actually, here space might be guaranteed O of n because of the string builder and how it works. Yeah, so serialize the string builder is going to have to be O of n, but the deserialize helper will have space of O of n because of the list. Okay, so it's both O of n. Space and time is O of n for everything. O of n. O of n. Yeah, but we're looking for worst case because of the string builder. O of n. O of n. The Q, yep. O of n. Yeah, okay, we're cool. Oh my gosh, I need to do this. Okay. Yeah, times O of n log n because of this. Space is, that's constant actually. Yeah, space is O of 1. Okay, I think we can remove task scheduler from the list here. Oh. Interesting. Okay. That's cool. I don't even need to do these two. I think this is good too. Distinct subsequences. Here. I might do this tomorrow. Yeah. Okay. So we gotta. I'm happy with the progress we made today, but I do think I could have been a little bit more efficient with everything, because I mean, we watched that useless Leetcode video that I thought was going to teach me some other stuff, and then yeah, we got through all of backtracking, but I understand, like, I actually understand how these problems work now. Almost all of them are 2 to the power of n. Some of them are, like, I think words palindrome partitioning is like 4 to the power of n. No, this is 4 to the power of n. But most of them are a certain number to the power of n, if not 2 to the power of n. Almost all of them are that. We went through all of trees, actually. And then went to all of trees and got, what do we get? We dialed down space and time complexity, basically. I mean, there are a few interesting problems like subtree of another tree and kth smallest element in BST, but we were able to actually optimize kth smallest element to guarantee log n space rather than having log n or n space. And then subtree of another tree, we messed up one of the problems. So yeah, and then reviewed a few of these. Yeah, I mean, I do think we could have done a little bit more, but I could have done a little bit more. I got distracted a little bit with a few things going on my other screen, and then I wasn't thinking as clearly as I probably should have been, but not too bad. I'm happy with the work that was done. Let's see what our tally's at. 12:53. Okay, so yeah, just chipping away. I mean, eventually we're gonna, if we keep up at this rate, we'll be done with the Leetcode soon. I'm just honing the blade, making sure I know everything before I start moving on to other things and moving on to new topics. But yeah, pretty satisfied with all of that work. Yeah, if everything goes to plan, we should be starting to do new problems by Monday. I think tomorrow it'll be mostly dialing everything in and figuring everything out. But after that, I think we can start just destroying greedy advanced graphs we just need to relearn. And then bit manipulation, I think, will be easy once I get the hang of it. And I mean, I think each problem has a trick. So to be honest, I'm gonna spend like maybe 5 minutes per problem, and then figure out the trick, and then do it. And then, I mean, I'm pretty good at memorizing the problems after memorizing and understanding. More emphasis on understanding, but in terms of memory, like, I memorize the problems right away. So, yeah, pretty happy with that. Hopefully we'll get Leetcode done by the end of, I think it'd be realistic to say by the end of this coming week, we will get Leetcode done. So, yeah, that was a treat. Yeah. We'll move forward after that. Until the next one.